Welcome to the chapter 6, part technically 7 and 8. So we did an activity for part 7 that was transformations, and we're going to look at it really quickly from a notes perspective. But really, that activity was where you should have been jotting down your notes. And then we'll look at part 8, which is inverses. Now, this is the last section of notes for this chapter. So we're coming up to the chapter test. We have the review, and then we have the test next week. So make sure if you have any questions, you're reaching out to me. Next week is parent contact week. So I have my office hours blocked out. So everything needs to be scheduled as a question. If you'd like to schedule office hours, send it to me as a request. I would like to schedule office hours with you at this time. Are you available? And I will let you know on a case-by-case basis, because I do need to keep some time set aside in case I have any parent meetings next week. Okay, so our focus today, we're going to look briefly at transformations, graphing radical equations, and then we're going to look at inverses, understanding what it means to be an inverse, finding an inverse in 3 different ways: from a set of points, from a graph, and from an equation. And then we're going to look at function composition of inverses. Remember, we did function composition a couple of classes ago. So starting out, transformations. This is the activity that you just finished last class. Transformations for radicals are exactly the same as all the other functions that we've looked at. So we've looked at lines, absolute values, parabolas, as well as polynomial functions. We've been looking at it almost every chapter. We've been looking at transformations. So my hope is that by this point, we're getting more comfortable with transformations. They're very, very important. Okay. And we can start seeing that these transformations are going to be the same for any relation. So even if it's not a function, if we have a graph of something, we can translate that graph by using these same transformations. And the way that we can denote that, for radicals, we have the square root or the nth root. We have the parent function as just the root of x. So no transformations, no numbers, no addition, no coefficient, just the root of x. And then to reflect it, we saw this in the activity, is a coefficient. So we need to multiply that root by -1. That's going to reflect it over the x-axis. That's going to make it upside down. Okay. If it's not a reflection, maybe it's a stretch or a shrink, it's getting skinnier or wider. And this could be in conjunction with a reflection. So it could stretch and reflect. Then we have a coefficient of a. So not necessarily a 1 or -1. It could be 2, it could be -4, right? And that's going to reflect and stretch. So that's what the coefficients do. And then we're a little bit more comfortable with translating, moving the graph horizontally by h. And remember, if I have x minus h, I can solve x minus h equals 0, x equals h. And h is going to be the x coordinate of our vertex. And remember, the vertex is the point of change. So for a radical, and when I graph a radical, this point here is called the vertex, and we can call it point h comma k. Okay, and then k is just k equals whatever was added, and so our vertex is hk. If this was added, then it will be positive. If it's subtracted, it will be negative. Okay, if h was added, it will be negative. If h is subtracted, it will be positive. So h does that little sign change. That is transformations. If you want a little bit more practice, that activity is still available for you to review. You can't change your answers anymore, but you can absolutely still review it. Okay, so let's go ahead and talk about inverses. An inverse is the opposite. So what I want you to think of when you hear the word inverse, I want you to think opposite. Now, we've been using inverses for a very long time. If I tell you addition, what is the opposite of addition? The opposite of addition is subtraction. So we do actually have several inverses that we're already familiar with, right? So we said the opposite of addition is subtraction. What about multiplication? Well, I don't know why that keeps happening. Okay, what about multiplication? What's the opposite of multiplication? Hopefully you said division, right? And that means that the opposite of subtraction is also addition, and the opposite of division is also multiplication. Okay, so we have these inverse functions, And we use those inverse functions when we're solving for variables a lot. But now we want to find the inverse when I have multiple operations together. Okay, so think about an inverse as the action that would undo another action. When we're talking about inverses, we have some special notation. We have f of x is a function, then f inverse of x is written with this little -1. Now this looks just like an exponent, but it doesn't mean the same thing as when we have something raised to the -1 power, right? So if I had x to the -1, I would say, oh, well, that's the reciprocal of x. But if I have f to the -1 of x, this does not mean 1 over f of x. In order to write 1 over f of x, I would write f of x to the -1. So notice the location of that -1. If it's next to the f, it means the inverse, which is not the same as the reciprocal unless the only operation is multiplication, because we said multiplication and division are inverses. So if the only operation was multiplication, that would work, but that's going to be very, very rare, okay? So we want to be careful with that notation. If I'm looking at a reciprocal, it's going to be outside of the function notation. If it's within the function notation, it means inverse, okay? And what is an inverse? Well, an inverse is when we have an ordered pair AB, A is the input, B is the output, then to undo that, I should be able to take B and get A back, right? So to do something is to go from A to B, to undo it is to go from B to A. So if the ordered pair A comma B is in the function, right? So that means in my XY table, if A is my X value, then B is my Y value. Then for the inverse, for F inverse of X, if B is my X value, then A must be my Y value. So I have this little image here to kind of take it out of just a mathematical perspective. And this image is showing you that stapling and staple removing are inverses of each other. If I put a staple in, then taking a staple out is the opposite, the inverse. Okay, there are a lot of examples like that. So I'd like you to think about what is an example in everyday life that you can think of as an inverse, something that's the opposite, something that if you do it, you would do the other thing to undo it. Okay, think about something like that. I'd like to see some of those examples in Edpuzzle, please. Okay, so how do we calculate these inverses? So to find inverses, what we're looking for is if we have an ordered pair, we're switching really the X and Y values, right? We had said A comma B would have the inverse B comma A. So whatever my X value was and my Y value, I'm going to switch them. So that means if I have a relation, now remember, relation is just our general term for function that we don't know if it's a function. Okay, so if my domain is 1.2 to 1, that gives me the ordered pair 1.2 comma 1. And then I have 1.4 comma 1, 1.6 comma 1, 1.9, whoop, that one should be a 2, comma 2. Okay, that's the ordered pair represented by this relation. The inverse of it, I'm going to switch the X and Y values for each of these. It's going to be 1 comma 1.2, 1 comma 1.4, 2 comma 1.6, 2 comma 1.9. So all I did is I switched my X and Y. The X became Y and the Y became X. So let's go ahead and try this. We want to find the inverse relation of S. S is given to us in an XY table. So to find the inverse, I need to switch the X and Y. My first point is 0, -1. So the inverse of that will be -1, 0. My next point is 2, 0. So the inverse will be 0, 2. The next point is 3, 2. So the inverse will be 2, 3. And our last point is 4, 3. So its inverse will be 3, 4. Now I want to know, how can we tell if these are functions? Are either S or S inverse functions? Well, a function, right, had to pass the vertical line test, meaning that the X values do not repeat. So in order to have this be a function, the x values for a function do not repeat. Do any of the x values repeat for s? They do not. So s, yes, is a FCN stands for function. S is a function. How about S inverse, or the inverse of S? Do any of my x values repeat? They do not repeat. So yes, S inverse is a function. Okay, so both S and S inverse are functions. Now, we could see in relation S, none of the y values repeated. So we knew that S inverse would have to be a function, because in order for the x values for S inverse to repeat, the S values of X inverse, the inverse of S, the X values were originally the Y values of our original relation. So if the original Y values didn't repeat, then the new X values will not repeat. Okay. Lastly, we're going to look at looking at these points on a graph. Okay. So first, let's graph relation S, and I'm going to graph it in blue. Relation S. So I'm going to plot the point 0, -1, 0x, -1y, and then 2, 0, 3, 2, and 4, 3. Now we can see that this is not a straight line, right? It's pretty close, but it's not quite a straight line. That's okay, because what I'm interested in is graphing that and seeing how does that relate to its inverse graph, which I'm going to do that in green. The inverse of S in green. So we're going to go to the point -1, 0. -1 is our X, 0 is our Y. Be careful of that. 0, 2, 2, 3, and 3, 4. So what's happening here? It might be a little bit hard to see at first, but if I connect each point with its inverse point, it might be a little bit easier to see that these are all lining up parallel to each other, right? So there's actually this line that goes right through all of those connections, and that line is y equals x. Since we're switching the x and y values within our points, what we're graphing, what we're actually doing is we're creating a reflection over the line y equals x. Okay, so when we're looking graphically at what is an inverse, if I'm looking at a picture, what I want to do to see if it's an inverse is kind of tilt my head to the side a little bit. If I tilt my head to the side a little bit, I should be able to see this axis of symmetry along the line y equals x. Not y equals 0 or x equals 0, right? Those are our axes, but the line y equals x, which is a diagonal line. Let's look at another example. I want you to go ahead and try this. I gave you a new relation. We'll call it T. I want you to find the inverse of T, graph T and T inverse, and then tell me if they are functions. Okay, so go ahead and do that, and then we'll look at the answer together. All right, let's take a look at it together. So the first thing that we want to do in order to graph T and its inverse, we need to find T inverse. So all I did is switch the X and Y values for each point. Then I graphed those points, and we can see at that point, either from the table, looking at if X values repeat, or from the graph, looking at the vertical line test, that the red, or a T inverse, is not a function because we have 2 points that are on top of each other, but the blue, which is T, is a function. So it doesn't necessarily mean that one will always be or one will not be. And if one is a function, the other one doesn't necessarily have to be a function. We have to check them independently every time. And then I drew my little axis of reflection, that yellow line, so that we can see, if you kind of tilt your head to the side, you can see that axis of reflection. Okay, you can see the symmetry there. Okay, so let's take a look at our next idea, I guess. We've already been looking at the graphs, but let's go ahead and look at graphing f of x equals x squared, okay, using at least 5 points. And then we want to find f inverse by using those same points. And then we're going to have a couple questions. So the first thing, I'm going to go ahead and start by using red for f of x equals x squared. So let's start with 0. 0 squared is 0. Nice and easy. 1 squared is 1. And then I can also do 2 squared is 4. Not too bad. Let's go ahead and do -1 squared, which becomes a +1. And -2 squared, which becomes a +4. Okay, now I don't have to keep going. I'm going to do one more. 3 squared is 9, just to kind of use up the most of my graph. And I know the axis of reflection will give us -3, 9 as well. Okay, so this is x squared. So now, without making a new table, I want to try and use the points to graph f inverse. So I'm going to say, okay, 0, 0 will be the same if I switch the x and y values. 1, 1 will be the same if I switch the x and y values. 2, 4 will change. It will become 4, 2. -1, 1 becomes 1, -1. Okay, so you can make a new table, absolutely, but you can also kind of visualize what's happening, right? If I reflect this, and I'm going to draw my line again, over the line y equals x, and remember, a reflection means I'm going perpendicular to that line the same distance. Okay, so from my next point, I can go with a slope of -1. That was 3 diagonals across. So I'm going to go 3 diagonals across. That should be my next blue point. And indeed, -2, 4 would become 4, -2. Let's do another one. So from my point 3, 9, going with a slope of -1, I do 3 diagonals. So I go across 3 diagonals, and there should be my point. That was 3, 9, and it became 9, 3. And let's do one more. We have -3, 9. So I'm going to go down with a slope of -1 because that's what's perpendicular. Okay, that was 1, 2, 3, 4, 5, 6 diagonals. So I'm going to go 1, 2, 3, 4, 5, 6 diagonals across. And that should be my new point. And it is indeed 9, -3. So do we see how we are using our reflections from geometry to kind of help us? If you're not comfortable with those reflections from geometry, that's fine. I want you to be able to visualize it at least, but you can always calculate those points by just switching the x and y value. And the reason we can do that is because we're reflecting over the line y equals x. So what used to be x is now y, and what used to be y is now x. Essentially, we are substituting. Okay, so let's look at first the graph of x squared was a function. Is our new graph, is our blue graph a function? No, it does not pass the vertical line test. Does not pass the vertical line test. I'm going to abbreviate it because we've talked about this before. VLT is vertical line test. What does that graph, what does the blue graph remind you of? Hopefully, it reminds you of a square root of x, but also a negative square root of x. Okay, if we think back and we remember, if we had y equals x squared and we wanted to solve for x, remember we could take the square root of both sides, but then we have to do a plus or minus. And that's where this plus or minus comes from. Okay, we're going to get more into that in just a second here. But hopefully that blue graph reminds you of the square root graph, because that's exactly what it is. But why is the square root graph only half of our graph, right? How can we have two pieces, the positive square root and the negative square root? Well, we wanted to call the square root a function. And in order to call the square root a function, it must pass the vertical line test. That means no matter what x value I put in, every single person gets the same square root of x. And this is where, at the beginning of the chapter, we called these principal roots, principal roots and negative roots. And that is exactly why we have principal and negative roots, is so that we can have functions with the square root of x. Okay. So let's take a look now at finding the inverse equation. So I alluded to this on the last slide. If I want to find the equation inverse f of x equals x squared plus 1, what we first need to do is rewrite, I'm just going to copy it first, x squared plus 1. We need to rewrite this in terms of y, because right now we don't have a y, we have it as f of x, two names for the same thing. So I'm going to write this as y equals x squared plus 1. And then I'm going to do a line underneath that, or you can start in a new column if you'd like. There needs to be some visual indication that we are no longer working with the same function, because what I'm going to do is replace x with y and y with x. And just like what we were doing with the points, when we switch our x and y, we are creating the inverse function. So this is not f of x anymore. As soon as I switch my x and y, x equals y squared plus 1, this is now f inverse of x. So I want some visual indication, whether it's a line across the page or starting in a new column, using a different color, some visual indication that this is now a new function. I should say a new relation. I don't know that this is going to be a function. And now, because I want to write it in function notation, I need to solve for y. So I'm going to subtract 1 from both sides. X minus 1 is y squared. And this is what I was talking about on the last slide. Now I can take the square root of both sides, but when I do that, I need to make a plus or minus. So now I have that y equals plus or minus the square root of x minus 1. And our last step is to write that. The reason we give y a different name is so that we can tell it apart from other y's. So we're going to name it f inverse of x. The negative one needs to be next to the f and not next to the x, equals plus or minus the square root of x minus 1. Now we've seen the plus or minus notation before. It means that there are actually two answers. There are two functions here. F inverse of x is the square root of x minus 1. And f inverse of x also equals negative square root of x minus 1. Okay, so if we were to graph, I'm just going to do a quick graph of x squared plus 1 goes up by 1. Then the graph of square root of x minus 1, x minus 1 equals 0, so x equals 1. There's that graph. And then in a new color, I'm going to do this one. X again equals 1, but that one's negative. So do we see how it takes two functions to make the inverse of our x squared parabola? The red one and the green one together are not a function, but by themselves, each one is a function. Okay, now these steps 1 through 4, make sure you have them written down somewhere, because those are going to be the steps to find the inverse of an equation every time. Let's look at another example. I'd like you to try this. Graph f of x equals the square root of x minus 2 and its inverse. Then find the equation of the inverse to verify the graph. Okay, so first graph it and find the inverse, then find the equation and verify it. And then we'll look at it together. Okay, so I started by graphing f of x, reflected those points to get f inverse of x, and then I solved the equation. Now, when I solved the equation, I got x squared plus 2, but shouldn't that graph also have kind of a left-hand side here? Well, what happened is we aren't reflecting an entire parabola. We're reflecting a square root function. So we don't have the left side here. The way we indicate that when we write our function is we say that this is only true for x greater than or equal to 0. Okay, so this is a new thing that you have to write when you're only working with part of a parabola. You're going to indicate that you're working with either the right side or the left side of the parabola. X is going to be greater than or equal to 0, or sometimes it might be less than or equal to 0. Okay, how do we know which one it will be? Well, if we look at our original f of x was a square root, and square roots have to be positive, right? If it was a negative square root, then it would have to be negative, because we can't take the square root of a negative number. That would be imaginary. So what is the domain of f of x? F of x is our blue one. The domain is from 2 to infinity. I'm not going to go into too much detail because we did that in the activity. For the red one, f inverse of x, our domain starts at 0. So that is from 0 to infinity. How about the range? Well, the range for the blue one starts at 0 going up. So that is from 0 to infinity. And the range for the red one starts at 2, ranges the y values, so from 2 going up to infinity. If you notice, the domain and the range switched. That makes sense because our x and y values switched. So the total interval of x values should switch from being the domain to being the range. And all of the y values switched from being the range to being the domain. So the domains and ranges should be the same, but switched. Okay. All right. This is the last topic for today, composition of inverses. Remember, when we were composing functions, that means substituting a function into another function. Okay. So the first step here is I want to find the inverse function because we're going to compose them together. So we have f of x why isn't it writing? F of x equals 1 over x minus 1. Y equals 1 over x minus 1. Substitute that into x and y switch. So that's x equals 1 over y minus 1. I'm going to do this as a ratio so that we can just reciprocate both. So that means kind of like cross multiplying, right? I'm going to multiply across. So we get that y minus 1 equals 1 over x. And I can put that over 1 if that helps you visualize that. And then plus 1 on both sides, plus 1, y equals 1 over x plus 1. I'm just going to leave it like that, okay? So f inverse of x equals 1 over x plus 1. Now we want to compose my functions. So we have f of f inverse of x. First thing that we need to substitute is the f inverse of x, and that is 1 over x plus 1. And we're going to substitute that into our original function, 1 over x minus 1. And instead of x, we put 1 over x plus 1. Okay, now we're going to simplify. Plus 1 minus 1 is just 0. So we have 1 over x, and we talked about keep, change, flip. 1, division turns to multiplication, flip becomes x over 1. So our composition here equals x. I did something and then I undid it. So my output should be my original input. That means that those acted like inverses. In order to verify that they truly are inverses, I need to do it both ways. So now we're going to do it the other way. F inverse of f of x. So that means we're doing f inverse of, what does f of x equal? 1 over x minus 1. And then f inverse is 1 over x plus 1. And my x is 1 over x minus 1. So we're going to again do keep, change, flip. 1 times x minus 1 over 1 plus 1. This becomes just x minus 1 plus 1, which is just x. If both of those equal x, then we know for sure that those two functions are inverses. Now, we just found that they were inverses, but that's a good way to check your work, okay? It's a good way to check your work is to just substitute one into the other and then do the other way around. And if both of those equal x, then you know you found the correct inverse. Okay, I know today's lesson was a little long. That's it for today. And because it was a longer lesson, you only have 3 problems to do on the lesson check. Okay, you're just finding the inverse and determining if it is a function for each of those 3 functions. And then I will see you next class.